The chemical principle of energy levels and electrons' excited and ground states describes the way in which electrons can emit energy. This occurs when electrons are exposed to a high amount of energy and move up energy levels before returning back down to their ground state, and in the process of doing so, they emit energy. The energy levels, or quanta, within each specific element explain the different varieties of electromagnetic wavelengths that can be produced, many of which can occur as visible light. This is evident through the Jablonski diagram shown on the right. In the following experiment, this chemical principle was explored through the heating of various metal chloride salts. The coloured flame that was produced gave an indication of what metal ion was present in each solution. They showed the way in which electrons jump up energy levels when in their excited state, emitting energy in the form of light as they progress back down to their ground state. To conduct this experiment, a spot plate was prepared using distilled water to rinse any leftover contaminants from previous use. 6 to 8 drops of each solution was placed into each indentation in the spot plate, and the location of each solution was recorded. A Bunsen burner was lit with a hot flame, and the test wire was dipped into hydrochloric acid and heated with the Bunsen burner to remove any contaminants. This wire was then dipped into a solution from the spot plate before being heated in the middle of the Bunsen flame. The colour visible was recorded in the results table. This was then repeated with the other solutions, including 3 unknown solutions. After each solution, the wire was cleaned in hydrochloric acid to remove residue from the previous solution. Safety aspects that were implemented during this procedure included wearing safety glasses and lab coats throughout the experiment to protect the eyes, face, and body from the chemicals used. When the Bunsen burner was not being used, a safety flame was implemented to ensure that other individuals were aware that the flame was on. Great care was used when heating the wire and was not left on the bench unsupervised. To dispose of the chemicals, each well of the spot plate was cleaned with a paper towel, which was then disposed of in a bin. The spot plate was then rinsed with distilled water before being put away. The wire loop was left to cool before being put away. Hands were washed with soap after the completion of the experiment. As seen in the diagram, each element created its own unique colour. The table shows what compounds were used in the experiment and what results they gave. This chemical principle is implemented in real-life occurrences such as fireworks. A firework consists of gunpowder, an oxidizing agent, fuel, a binder, and a metal compound that produces the colour as it explodes. The gunpowder causes the firework to shoot into the air. Another fuse inside of the canister ignites and causes it to become very hot. This causes the electrons within the metal compounds to absorb the heat and become excited before returning to their ground state and releasing a photon of light energy. The combination and arrangement of the metal compounds within each firework allows various colours and unique patterns to appear as they explode. The compounds used in fireworks are often the same ones as investigated in the above experiment. The principle of excited electrons producing energy is also significant in a laboratory sense, as it is a way in which scientists can determine what elements are present in a compound. The flame test can be used as a step in identifying unknown substances by recording what colour flame is produced when heated. Another technique that can be utilised is spectroscopy, which allows for the emission of energy from electrons to be measured and a spectra to be detected. This can be implemented in a medical sense by using spectroscopy to screen for metal in the body. Another way that this technique is evident in medicine is through laser surgeries, such as LASIK eye surgery. Energy produced by electrons becoming excited, then returning to their ground state, is concentrated into a laser which is used to cut and reshape the cornea, fixing vision problems. The previous examples outline how the chemical principle of energy levels and electrons' excited and ground states is implemented in real-life experiences and laboratory and biomedical sciences.